Hello to whoever is watching this video. I'm Krista, and in this video, I'm going to talk about using the MGF method to find transformations of random variables. And before we dive into that, I want to say a few things about why the MGF method is useful. So in this class, you have already been introduced to the CDF method and the PDF method. So they're both very useful methods, but they have some major limitations. So usually they work well for one-dimensional problems or two-dimensional problems. That is to say, they work well when you have only one random variable or only two random variables. Once you have three or more random variables, the CDF method and the PDF method become very complicated. Let's say if you have three random variables, to use the PDF method or the CDF method, you would be essentially integrating over a three-dimensional region, and that's very complicated. And if you have five random variables to transform, you would be integrating over a five-dimensional region, and we don't really want to do that. So usually for the high-dimensional problems, so for problems that have maybe like more than three random variables, we use the MGF method. And in this case, we have y1 all the way through yn, so we have n random variables. So the MGF method would be the natural choice to use. So let's begin. So y1 through yn, they're all Bernoulli. So what I would do is go to the formula sheet and pull up the Bernoulli MGF. So just let's pause the video for a moment to do that. So I pulled out my formula sheet and I found that the Bernoulli MGF looks like this. 1 minus p plus p times e to the power of t. So this is for Bernoulli. And the next thing we want to do is we want to find the MGF of W. And by definition, the MGF of a random variable is equal to the expectation of e to the power of t times this random variable. So in this case, it's the expectation of e to the power of tw. And w is defined as the sum of all of the yi's. So let's go ahead and replace w with the sum. So let's do some mathematical manipulations here. If we have e to the power of a plus b, we can split it up into e to the power of a times e to the power of b. So let's do exactly the same thing here. Let's split up the expression into e to the power of t times y1, e to the power of t times y2, all the way to e to the power of t times yn. And let's notice a very important detail here. y1 through yn, they're IID, so they're all independent. And if the random variables are independent, the expectation of the product is equal to the product of the expectations. And let me write this as the product from 1 to n of the expectation of e to the power of tyi. And let's take a look. What exactly is this? So let's recall for a moment, the MGF of a random variable x is defined as the expectation of e to the power of cx. So right here, what I have is the expectation of e to the power of t times a random variable. This would mean, by this definition, we know that this is the MGF of yi. Because let's see, the MGF of x is the expectation of e to the power of tx. So naturally, the expectation of e to the power of yi would be the MGF of yi. And let's go back to the question. Let's go back to the IID part. So y1 through yn, they are not only independent, they are identically distributed. And because they all have the same distribution, they all have the same MGF, which is the MGF of a Bernoulli random variable with parameter p. So let's go ahead and plug that in. So that's 1 minus p plus p times e to the power of t. And right here, we are taking the product of the same thing, of n of the very same thing. So when that happens, what we're actually doing is we're raising this expression to the power of n. So I would like to ask you to pause the video for a minute and go back to your formula sheet to see whether this MGF, if this MGF looks like one of the MGFs given in your formula sheet. And I would say yes, this is the MGF of binomial MP. The MGF has a very, very useful property, and that is uniqueness. The MGF is unique. So if the MGF of a random variable looks like the MGF of binomial MP, then this random variable is binomial MP. So by the uniqueness of the moment generating function, W follows binomial MP because its MGF is the MGF of a binomial MP random variable. And that will be it for this problem.